heat exchanger, but it's a special kind of heat exchanger. Now this is the jacket on the tank. It's right in here. Can't be that tough.
Is it also a filter?
No, no. Simply, it's a condenser. Remember that you're going to be running like E. coli or something in here. What temperature you're going to be running your E. coli at? What's that? 100 degrees. Okay, E. coli does not like 100 degrees. I don't care if it's C or Fahrenheit. Okay, it's close if it's Fahrenheit. Why do you know that? I'm going to give you the benefit of the doubt. Because you don't know. How about you? Human body temperature. Remember, E. coli is a thing that grows in your guts, and so 98.6/37 degrees Celsius. At that temperature, if you're blowing a lot of air through there, and just as a quiz, how much air are we running through the 300-liter reactor? You don't remember, okay? So you're hiding from me. How much is going through the 300? 300 liters per minute, 1 ppm. You can imagine if you're running 300 liters a minute through there for compressed air. Remember, when you compress air, it drops out the water. So if you have a home air compressor at home, when you compress it, you have a needle valve to bleed off all the water that comes out as you compress the air. And so it means that it would be relatively dry air going into that thing. If you were blowing it in and you're running it through there, you can imagine at 37 degrees it would actually evaporate pretty quickly. So this is just a condenser, is it all it is. Once we go across from the condenser, then we come into something else. So then the question is, what is that something else? We all know what this is, right? What is this thing here? That's the pressure flow restrictor. Okay? So then what is the next one over here? What is this thing here for? Let me back up one step here. What do you think this thing is right here, this big doohickey? It's a filter of some sort. What kind of a filter might it be? It's probably more like a carbon cartridge or something, because E. coli stinks. Okay. The other thing is, remember, you are trying to achieve not releasing your organism, but it turns out that's not really what that one is for, because you don't really have a way to kill it at that point. Okay. But if you take a look, it goes into the header. That's the actual vent, and then the stink goes upstairs, if you will. Okay. And so that's kind of what that's about. As we make our way back, it turns out that little unit there is actually your microbial sterilization filter. This little guy right here, inside there will be like a 0.2 micron filter that will keep anything from escaping the reactor. Okay, and if you look at it very closely, we'll talk a little more about sterility and so forth, but that filter can actually be sterilized using the steam that's used to sterilize this. Okay. And so that's what's going on there. So now back to this question. What is that unit, which is exactly the same as the one that is preceding the microbial filter on that unit as well? Let's see. Who have I not picked on yet? I haven't picked on you yet. Take
bigger filter?
No.
Bigger holes, okay.
No, it could be like a pre-filter. That would not be a bad idea. It's serving the same purpose of what you might have a pre-filter for. Why would you put a pre-filter before the 0.2 micron?
It's like clean out the bigger stuff.
So that
it doesn't clog.
So it doesn't clog. Yeah. Okay, so it turns out it's there to prevent clogging, but for an entirely different reason. Okay. And so what would be your biggest risk if you have a 0.2 micron filter of having it so that it no longer can pass gas through it?
Pressure buildup.
Would be water. If I have any water get onto something with that small, surface tension will make it virtually impossible to push any liquid or any gas through the actual sterilization filter. So here's one more way in which your system could fail, is that if I'm humidifying the air over here through that 37 degrees, and if I lose cooling water on my condenser, I will then start to have the that start to go through and condense and start to blind out the microbial filter, which means my flow restrictor can no longer cause pressure control back on my unit itself. Like I said, there's a 50 ways to fail. And there's 50 people in the class. So that means we have 100% opportunity. Okay. So the question then is what is it functioning as if it's not a pre-filter? What it's doing is in the back, red? It's a heater. And so what it's doing is it's taking the gas temperature. We tried to drop out as much as we could in the condenser, but now we're close to, we've cooled the gas, but we're very close to saturation. We can't have that when we're going into the microbial filter, and so we need to now heat the gas back up again so you're way below the point where condensation can take place before it goes through the actual microbial filter. You can imagine that that then operates all the time. So while I'm running the reactor, that unit goes through the process of always heating the unit. Now again, if I lose steam on that, I would then probably lose the run, because what will happen is I'll blind out the filter and I won't be able to actually recover from that. That leads then to one of the very basics of the design of these things. And remember, we have to run everything aseptically. Aseptically is a fancy word for only what you want is in there. A lot of times people refer to it as sterile, but it's not really sterile because obviously the tank's full of bacteria. Okay, aseptic design is something that I comment about in here, but you can take a whole course in designing equipment for aseptic work. Okay, I'm going to go over in here and I'm going to pull a bunch of little toys out of the cabinet, you can pass these around. Here, test your. There, you're good. Okay, some pieces and parts and so forth. You can hand these back as well. What I'm going to refer to here now is the basis of sanitary fittings. Okay, so these are the standard toys that you'll see in the food processing industry as well. And the basic design of these things is such that what you want to do is be able to, number one, make them so you can clean them. Because it's not just about running one run in here, but because if I would need to run a run afterwards, I need to make sure that all the bacteria are gone. And so what you have then is something like this where you have a fitting and you can put a gasket between the two. Then you can take another fitting, you place the two together, okay? And if you look at it very closely, these things are actually tapered. And that taper is referred to as a tri-clover fitting. And it was designed for this type of an industry where what you can do is you can take a tri-clover clamp that is made by, guess who? Tri-clover, except this isn't. It used to be made by Tri-clover. Everyone calls it a Tri-clover clamp because that's who originally made it, okay? If you look very carefully through the things here, you'll find some of them that actually have a clover leaf on them, and they are the bona fide Tri-clover clamps, but 90% of them are, who knows, okay? We call them all Tri-clover clamps anyway. And what it is that there's a little bevel inside there, and that bevel matches up with what's on there. And so when I take this thing and I pull it over onto the unit here, it very gently and pulls the pressure together for this thing so that I end up with an aseptic seal on that. And you'll notice that everything on this, from the condensers to the probes and all that, almost every one of them is put together with this type of fittings and so forth for two reasons. One is they can take a significant amount of pressure. This thing is not going to give out because of that. And they don't leak, because you can pull this thing really nice and uniformly snug onto that seal that's inside there and throw together all your parts and pieces for that purpose. So we can, as you finish up, don't take the Tri-clover home with you, okay? All these toys are exceedingly expensive, okay? And you can throw them into here, and we can worry about sorting them out later. Okay, I'm trying to remember where I was heading with the logic of aseptic design. Okay. An entirely different aspect of pressure control, remember, is that you want to actually sterilize these units. And so what you want to do is, of course, run steam into it. But if I was to run a lot of steam into an actual reactor, I would be wasting a huge amount of thermal energy. So instead, what you'll see is that on these units, so Katie, let's see, find me a steam trap on your unit. A steam trap. I picked on you because you're vertically challenged, okay? And so... No, it turns out that there's probably at least 15 or 20 steam traps on every one of these units. They're all over the place. Okay? And so, Erik, right underneath the microbial filter, that little thing right there, that is a steam trap. Over here, underneath every sample port, these are all steam traps. They don't look like much. They're just a solid round doohickey. Here's a steam trap right here. Okay? And you might ask yourself, you know, what is a steam trap? And a steam trap is very simple. What you do, there are different designs. One is a ball, but the easiest one to understand is you take a series of metal plates, and the metal plates are machined so that in combination with the thermal coefficient of expansion, if they reach 121 degrees, the sterilization of this unit, the steam trap will actually no longer allow steam to escape through it. And so what happens then is as you're steam sterilizing, for instance, this filter, okay, okay, which I knew that was, I was trying, here, okay, we haven't run this one in a while, okay. If I was to take that and allow the steam to go onto this unit, okay, it will clamp down on the steam, and then at that point it'll come to the source pressure of steam in the unit. And so on this unit, on the headers over here, there will be another Jordan valve, but is a real steam pressure regulator that you set that to the pressure at which you want to sterilize the unit. And then at any time in which I open a valve system and the steam, live steam comes and hits the steam trap will then clamp down on it and not allow the steam to escape. What it does is that as the steam condenses, it'll drip down inside there, and when the condensate hits it, it actually cools it slightly, and then it'll just chatter open and it'll spit out the condensate. And so that's a critical aspect of the design of an aseptic unit like this, is that those steam traps are everywhere after you want to actually do a sterilization. And so if you take a look at a sample port, and I'll be over there in a moment, but I'm going to hand it to this group here. Every inlet and outlet of this unit is functionally an autoclave. And so this is like a little mini autoclave that when I take that and I put it on it, all I need to do is open this steam line. So if I trace this back, it'll get back to the steam pressure regulator. I open that line, and then I open this line to the steam trap. It'll come to steam sterilization pressure on that unit itself. And here, you can hold the autoclave. Okay, so I want to make sure the people over here see what I'm talking about, is that this is in fact, this sample port is in fact a mini autoclave. Okay, and so by opening this line right here, I allow live steam to hit it, and if you look very carefully, there'll be teeny tiny little hole that the steam will come inside here. And then I open this valve here, and the steam goes down and hits the steam trap, and then that keeps that at autoclave temperature for a specified period of time. The process of setting up and running one of these reactors takes about 2 hours. Because you have to run steam through every single valve, every inlet, and you have to do it in a sequence that makes sense in terms of how the autoclaving takes place. In the case of like the microbial filter there is no steam inlet. So clearly the only time that you can sterilize that is when you have steam inside the jacket doing its sterilization. And that's when you open the valve to the steam trap there to allow you to do the microbial sterilization. One of the biggest things that chemical engineers do when they get out in industry is write that kind of a procedure. And that kind of a procedure is called what? SOP. Standard Operating Procedure. I think the thing for running this is probably about 20 pages. And you will go through and it'll tell you every single valve in exactly the order. And if this was something like the old school version of good manufacturing practices for drugs, that procedure, every single valve when it would be changed would require a signature and a second counter signature of somebody else verifying that that valve was changed. And then, you know, they a lot of this now, they do a lot of the logging and do it electronically, but at the pilot scale, they are trying to get the FDA to allow them to go through the process. But to give you an idea, when people would go through and finally have a process that was going to be producing a drug, the documentation of what needs to be done at that point would fill your house. You know, it would be 3,000 square feet of binders and so forth with signatures that all the time that every batch that was made, I know that this valve had 20 minutes of being steam on it. Now, one of the characteristics is that you can never trust anything. We learned that with the pressure relief valve, right? Okay, and so even though you go through the process and you open all the valves, that doesn't guarantee that it actually gets hot, right? Okay, so what would be the SOP for seeing if the thing gets hot? You don't want to say the most obvious thing. Touch it, okay? Okay, and you'll be like, this is, oh shit, okay? And so some guy's job would be to go through and burn himself on every single valve. Now that was not a very smart thing to do. And I was looking around here as I came through and I didn't see the alternative of this is a thing called a temple stick, okay? And basically if you look at some of these valves and the ones over there, it'll look like a kindergartner came in and you'll see like it looks like somebody who had a crayon. And it is. A temple stick is a crayon whose melting temperature is 121 degrees Celsius. And it has a little bit of graininess to it there so that if you put it across a piece of stainless steel, it kind of grates. But as soon as it reaches its melting point, it does a nice smooth thing like that. And so that temple stick will be part of your SOP because it gives you an entirely independent way of knowing that in fact you made that temperature, because just because you open the valve doesn't mean that some other valve didn't let steam get to your actual thing that you were actually working with. And that's part of this whole process of understanding that there's a strong degree of redundancy and so forth in the actual operation of the unit itself. I'm trying to think, how much time do I have now? Just so I mean, you know, obviously I could probably like spend a lot more time with the unit. This is the lecture, if you will, on this. And there's a lot more doodads on this thing than what I've gone through at the moment. But once you start to get a little bit of a feeling that, hey, wait a minute, this is a little sample autoclave here, that's in fact how it works. The other things that we would want to control on here, for example, would be temperature. And you think temperature is real easy, right? You just find some dial somewhere and you dial in the temperature, but it doesn't work that way. The temperature for the steam sterilization cycle, how is it controlled? Bercules, okay? Okay. So how do you control the temperature during sterilization cycle? Redundant question. I already said. Steam what? That's like about a 5. Okay, of course, that's how we heat everything, is steam, and so that doesn't really answer much.